Alabama. It might be quite different depending where you're joining us from. So good afternoon and welcome to the Tree Fund webinar series, today in conjunction with ISA's Southern Chapter. My name is Bo Broadbeck, an extension specialist here at Auburn University and chairman of the Board of Trustees at Tree Fund. I would first like to welcome you on behalf of the Alabama Cooperative Extension System, the outreach arms of Alabama A&M and Auburn Universities. As always, we are honored and excited to host the Tree Fund webinar series. Today, we, in addition to having a phenomenal speaker, Dr. Coder, we also have Mr. Russell King, our new CEO, who will provide the Tree Fund update and a few housekeeping notes for you as well. Real quick, I do have a few housekeeping notes as your moderator before I turn the virtual floor over to Mr. King. During today's webinars, please submit questions to the speaker in the Q&A box. If you have questions for the moderators, whether it be myself, Mr. King, or Monica, you can submit those to the chat box. The webinar today is being recorded, and this webinar will be available, give us usually about a day or two, on the Tree Fund website under their archived webinars. Dr. Coder has been gracious enough to provide us a list of citations for some of the topics he will be talking to you today about, and those will also be available underneath that archived presentation. Finally, the CEU policy that we have with ISA has changed a little bit from some of our past webinars. We will not be providing the CEU code this time. Instead, we will be submitting the attendance records of today's webinar directly to ISA on your behalf. What that means is when you registered, you provided your name and hopefully you provided your certification number. Based on the attendance for today's records, we will submit that for you within the next few days. If you did not provide your certification number, please email Monica at Tree Fund, and we can update that record before we send it in. So with that, I would like to turn the virtual floor over to our new CEO at Tree Fund to give us an update with what's going on around Tree Fund and also introduce today's speaker. Russell, the floor is yours. If you'll share your screen and
how's that look, Bo? Thank you very much. Hello, and I'm glad you could join us. I'm Russell King, the Tree Fund President and CEO, and it's my honor to welcome you to this webinar on behalf of the Tree Fund, the ISA Southern Chapter, and the Alabama Cooperative Extension Program. The Tree Fund is happy to co-present this webinar with the ISA Southern Chapter. Southern Chapter had planned to present this program at its annual conference this spring as part of its mission to advance tree care knowledge and practices through research, education, and professional development. So you'll want to be sure to mark your calendar for next spring's Southern Chapter Conference and Trade Show, and that is set for March 20 through 23 in Atlanta. The Tree Fund was created in 2002 with a mission of supporting scientific discovery and dissemination of emerging knowledge in the fields of arboriculture and urban forestry. We advance our mission by issuing research grants, primarily for applied research in how to better plant, propagate, and care for urban trees, providing scholarships to students in arboriculture, urban forestry, horticulture, and related fields of study, and funding for grade school kids' education about trees and environmental stewardship. Since 2002, the Tree Fund has granted more than $4.4 million for research and education. To see what we've funded through the years, you can visit the Research Archives page on our website at treefund.org. You can search by keyword or by a scientist's name. You can also scan lists of research projects that we've funded most recently. We have expanded our webinar schedule in response to the many cancellations and postponements of conferences and other educational meetings. We're proud to announce 4 new webinars, including today's webinar, that we're planning for the next 2 months, as well as our slate of webinars for the rest of the year. You can, of course, find the full schedule on our website. We're committed to bringing you even more of these webinars so you have opportunities to earn your CEUs. As you know, we offer these absolutely free. The Tree Fund is a charitable foundation that is entirely funded by donations. So if you can, after the presentation, please go to treefund.org, click on the Donate Now button, and help us help you by making a donation. Your support really will make a difference. One last housekeeping item before I introduce our speaker. In accordance with the ISA guidelines, the Tree Fund will submit your name and ISA certification number to ISA for your CEU credit. If you did not submit your ISA certification number during registration, please email Monica at the address you see on your screen and give her your ISA certification number. And remember, you have to watch the entire webinar to qualify for CEU credit. So now it's my honor to introduce our presenter for today, Dr. Kim Coder. He is a professor of tree biology and healthcare and a Hill Fellow for Distinguished Public Service and Outreach at the Warnell School of Forestry and Natural Resources, University of Georgia in Athens. He holds degrees from Iowa State University in forestry, tree biology, and forest ecology. He was elected world president of the International Society of Arboriculture and served as president of the Southern chapter of ISA, the International Arboriculture Research and Education Academy, and the Georgia Urban Forest Council. Dr. Coder was appointed to the USDA Secretary's NUCFAC, advising on community forestry issues. He's the first person to receive 4 of ISA's World Awards, the Shigo, Harris, Lilly, and Merit Awards. He's won the Arbor Day Foundation's highest award, the J. Sterling Morton Award. He is also the author of more than 500 technical publications and articles, as well as an international lecturer and consultant to private citizens, corporations, attorneys, and communities on tree health, tree anatomy, abiotic tree stress, lightning and tree protection, storm damage, biomechanics, and community forest ecology. Welcome, Dr. Coder.
Very good. Well, good afternoon, everyone. You'll notice that I am in my pandemic beard. I have become quite lazy, and I don't know if I should share this, but this is the first time I'm wearing pants in days. So anyway, we are going to talk about trees today. And this would have been the starting talk at the Southern chapter. I wish we had met in beautiful Winston-Salem for the Southern chapter back earlier in spring, but these are strange and wonderful times. So we are going to talk about how trees work in storms. And if you go to this, just type in Warnell Outreach Publication site, you can download a bunch of stuff that will bore you to death on tree stuff there. And that all the literature I'm citing today is going to be at a list, a PDF list, when they archive this particular webinar at the Tree Fund site. So you can get all of these citations. You'll see them off to the side on many of the screens. This is Disney World. This is a tree that was designed to handle hurricanes. It's designed to become up to a Category 3 hurricane undamaged and be able to handle up to a 5, but it's made out of plastic, so we don't have to worry about that. The other thing we need to remember is that all trees fail eventually, and early, middle, or late, they'll all fail, and what we're going to do is have the best tree for now and in the near future. So today we're going to talk about load on trees, how they hold that load, how they change to hold the load, and then what we can do as arborists to treat them. Now, major storms that we have out there, we have thunderstorms, hurricanes, glazing events, or ice storms, tornadoes, derechos, and lightning would have been the second talk we had at Southern Chapter. I'm not going to cover that today. We're just talking about the actual wind and gravity loads on trees, not lightning damage. You'll have to have me come back sometime and we'll talk about that. Remember what tree structure is. It's a large sail area that's held upright in the wind on a tapered mast woven into a horizontal root plate. The environment just hates anything more than 2 inches above the ground. So the environment is trying to knock trees down and step on their face. The environment resists growth, and the genetic potential of trees tries to continue to push forward. So there's our tree. Number 1 is a wind load center, and number 2 is the center of gravity for the tree. And we have wind pushing as a lateral push onto that tree crown. And we have a number of measures that we've traditionally used. Frontal area is the area of the crown that is open to the wind that the tree sees. General height or crown height are different things. We also have a root plate, a structural root plate that helps hold the tree up. Remember what storm winds are, because we're primarily going to talk about lateral loads, wind loads, because most trees do not fail under gravity loads unless they're leaning, hillsides, or things radically change around them. So we're going to talk about wind loads. Remember that the root plates wobble. They move up and down 1/3 to 1/4 of an inch. Actually, at the base of a tree, they can be separated from the soil that they're attached to. So they wobble, the stems sway, the parts twist and bend. We can have fatigue between roots and the soil in the stem, concentrated around old faults, new faults. So either the parts or the soil are going to fail the tree, and then we have the catastrophic failure. In this case, the roots in the soil in a tornado. This was an EF4, popped them right down. We need to remember that even though the public sees wind speed in miles per hour or meters per second, we need to worry about force. It's force, not speed. So we are worried about the pounds per square foot, if we're usually using English measures, that are placed on the frontal area of our tree, on our tree crown. So the wind speed is something the weather people can give us, but it is the wind pressure that we're worried about. And when you look at wind force, the pounds per square foot of foliage and crown and stem, it rapidly goes up as we increase wind speed. And so just a little bit of wind speed increase, whether it's sustained or a gust, can provide tremendous loads. Now also remember that if we double wind velocity, we are quadrupling pressure on the tree. So again, just tiny changes in speed generate tremendous pressure on our trees, the load on our trees. And trees, because the bottom is rigid and the top can be very flexible, it reconfigures itself. It is moved downwind. This reconfiguration or streamlining is a very important component of helping a tree survive. If we look at crown reconfiguration, don't worry about the index value. There's the wind speed. The third column is the pressure put on every square foot of the tree crown, and the stem. And this is the tree crown reconfiguration value. We hit 100% around 55, 56 miles per hour, or around 8 pounds of pressure. If your drag coefficient is 1, we'll talk about that later. But 55 miles an hour, we have pretty much gone through all the tree can reconfigure. Now, if we have ice, an ice storm or a glazing event on the tree, we hit that level at about 30 miles an hour. But that is when the tree is reconfigured or it's gone through a streamlining as much as it can. Remember, here is our wind speeds on the left-hand side. Here are the pressures per square foot. And we have T1, threshold 1, and threshold 2. T1, the first threshold is where we have gone through reconfiguration. We have reached the end that we can't reconfigure anymore. And so this is called elastic reconfiguration. So we're bending back, we're streamlining against the wind. T2 is around 95 to 96 to 105 miles an hour. This is called brittle reconfiguration above that because we start to break stuff, big stuff. But T2 is where we've really ran out of tree safety factors. So as we get reconfiguration, then we get brittle reconfiguration up to the second threshold, and beyond the second threshold, it is amazing. It is fantastic that trees make it above 105 miles an hour of sustained winds, and they always do. A bunch of them go down, a bunch of them stand up, and the ones that stand up, it's just staggering that they do that. This is the proportion of trees that are wind thrown. We have, in this particular author's case, they went ahead and said relative storm severity. And so 50% of the trees go down when we hit this 0.7 in this particular author's storm severity. Now, again, you'll notice that the citations are going to be somewhere on the screens. You will be able to look these up when this talk is archived. There'll be a PDF there, and look it up. We have changed a lot of stuff in the last 4 years. The last 4 years of research in storms and tree biomechanics have been fantastic. There's been so many things that have been developed, and that is what I'm primarily going to talk about the rest of the day. And I'm going to, in your citations, most of them are from the last 5 years. Also, when we think about storms, it is the gusts that load them and the calms that unload them. And at higher winds, we don't necessarily come back, depending upon the wind frequency and speed, we don't necessarily come back to an equilibrium position. We're doing figure eights or big circles to leeward as the storm winds gust and calm. And trees can break and have been seen to break on the calms. When Hugo banged ashore in out of the Atlantic into South Carolina, north of Charleston, if you took an aerial view of that, most of the trees lie with the wind, and a few of them, about 1%, lie in the opposite direction. They failed in the opposite direction. And when you have a Category 4 hurricane, how do they fall the other way? They fell on the calm. This is a railroad solution to tree biomechanics. Those yellow things are railroad rails that this particular city decided, well, we'll keep people from bumping the tree and keep them upright. And this is a major port city, major southern state. Can't tell you which one. A host of the 96 Olympic yachting events, but they still have this. It's quite interesting. So let's take a look at storm loads. Here is the annual thunderstorm days for the United States, the lower 48. These are days where you can hear thunder. That's how the Weather Service does this. These are annual thunderstorm days. And in those thunderstorms, we can get a lot of wind. And we have different wind characteristics from something called air. And along the bottom is the Beaufort wind force. We can have breezes and gales and storms. And finally, at force 12, we get the hurricane. We can have a fresh breeze as opposed to things like a stale breeze, I guess. But the important thing for us is there's our force value on the far left-hand side, miles per hour, and load. Now, this load is not part of the Beaufort wind scale. I put these in. This is the pounds per square foot that you get. And notice that, and it's the midpoint load. And you notice here's the names. There's our fresh breeze there. But as we get farther, or the wind speed gets higher and higher, we increase the load on our trees. Notice force 6 versus, which is 25 to 31 miles an hour, strong breeze. And we get up to the 39 to the 46 mile an hour at force 8. We've more than, we've doubled our miles per hour, but we have more than quadrupled our load actually on the tree. What about tornadoes? Tornadoes, here is our, again, the lower 48 in the United States. These are tornadoes per year of what you can expect. You notice in the Midwest, Oklahoma, Kansas, a touch of Nebraska, Missouri, and Iowa. And growing up in central Iowa, I thought we were a little bit higher than this, but this is the NOAA Weather Service map. Number 6 is Tornado Alley. But you can get tornadoes, and especially if you have hurricanes, some of them can be spawned out of those. And here is our storm categories. These are the EF numbers that are used, wind speeds, and the mid-range wind pressures. And notice in these tornadoes, we climb quite rapidly. For the EF3s and above, we're getting 60 pounds per square foot. Now, the way to think about this is if I give you a 4x4 sheet of plywood, and that's 8 square feet, right? 4x4? No, that would be 16 square feet. However you do the math, think about, can you hold that against the wind when it's a 20-mile-an-hour wind? What about a 40-mile-an-hour wind? What about in an EF3, 150-mile-an-hour wind at 60 pounds per square foot? 60 pounds per square foot at that speed. You are going to be blown away like many of our trees are. This is a major port city, major capital, or major port city, major southern state. Can't tell you which one. They have a lot of old trees. You notice that in the, we've had a lot of included bark. We've had some decay, discolored wood, and we have a little thin bit of good wood that was trying to respond, prevent notch fractures, failures, and try to keep itself together. And in this case, it failed. And the rest of the story here is there was a beehive in this particular one. And that's why I'm standing across the street to take this picture and fled. Hurricane landfalls over time. If you stick out, and I'm sorry for everybody else, this is going to be Eastern North America, because remember, this was supposed to be for Southern chapter. But here's the hurricane landfalls over 50 years, historic landfalls. And if you stick out into the Gulf or the Atlantic, you have a very good chance of being hammered by a hurricane. Yes, even up if you're in Maritime or Maine, you can still be hit. And of course, the one state in the United States that sticks out into the Gulf and the Atlantic is that great state of Florida. And in their case, they're always getting from the left, from the right, up the middle. It doesn't matter. They're always getting hit by hurricanes. Here are the categories for hurricanes. Cat 1 and 2, go on from where Beaufort wind scale left off. And of course, 3, 4, and 5 are considered major hurricanes. So as we get above 111 miles an hour of sustained winds, that is considered a major hurricane. With changes that we have, that we're seeing across the globe, as we get more super typhoons, more category 5s that are creeping up there, maybe within the youngest participants' lifetime, we may see a category 6, although Dr. Simpson doesn't want that. Here's our storm categories. Wind speed, the same as I just showed you, but this is, again, the mid-range pressure on our trees. Pounds of pressure per square foot on the frontal area of our tree. And so if we have a Cat 4 come in, it's 54 pounds. How many square feet is in a medium-sized urban tree? Now I have to show this one because Weather Service, NOAA just came out with this little round handy dandy guide to damage potential. And it's kind of a neat little thing. You have the category numbers for hurricane, wind speed, relative wind force, and remember that goes up to the square. And then we have damage potential, which goes up to the 8th power. And the weather folks are trying to say, even within a category 4 hurricane, just 5 miles per hour can produce tremendous more damage than what you had before. So go to the weather NOAA's area and look up some of those neat little guidelines. Now, some people say, look, I don't live along the coast. Why should I care? Because a Category 3 landfall can have 60-mile-an-hour sustained winds this far inland. Look how much of the population and how much of our urban forests in the eastern United States are within that 60-mile-an-hour sustained wind. We have had some inland cities decimated by landfall of hurricanes along the coast. As we project over time, we look at the past, and we are getting more and more Category 4s and 5s spinning up in the Atlantic and the Gulf. Some of them are spinning up very quickly. Michael, that hit Georgia and Florida, it was in the southern Gulf and popped to Category 4 or 5 by the time it got here. Hurricane intensity has increased over the last 30 years, and the future projections for hurricanes are not that there's necessarily more of them, but they are going to be more intense. Larger peak winds, more heavy rains, and more energy. This was University of Florida took a look at a number of hurricanes as they came in off the Gulf and Atlantic, and they made a great graph of urban forest loss, percent of the urban forest loss versus wind speed. Some great information. Now, the other thing that comes with the hurricane is storm surge. And you say, well, now, just a minute. Why do we care about storm surge in trees? Because that salt water, the salt and the force that it's presenting can be significant for damage. And here's the storm category. 3, 4, and 5 are major hurricanes again. And you can have tremendous storm surge. And remember, a storm surge is not a tidal wave. It's the water that comes up around your feet. As much as, in this case, in Camille, 3 feet per hour to reach 25 feet of a surge. Here are selected hurricane surge levels that I pulled out from this source. There's Katrina had a 27-foot storm surge. Serious tree damage. Let's talk about ice for a moment. Ice storms are different because a bunch of the ice is about stiffness and gravity loads as well as wind loads. Here's the days per year with freezing precipitation. And here is, from a risk analysis point, this is ice thickness for a 50-year storm, for a 50-year ice storm. And you can see that in the beltway between the four-corner area of Kansas, Oklahoma, Arkansas, and Missouri, clear up to across to northern Ohio, that is a tremendous ice belt. But also, if you look at wind gusts in ice storms, so this is wind gusts in ice storms for a 50-year storm, the upper Great Plains with 60-mile-an-hour wind gusts during ice storms. And the wind is important. If you take a look at the National Ice Accumulation Index from our good friends in Oklahoma, this wind index gives you wind speed along the bottom in miles per hour and ice accumulation in inches. If you are running 4 or 5 in ice accumulation index, you are going to have massive tree damage. Here's accumulation on trees that we use as a rule of thumb. Freezing rain is on the left-hand side, how many freezing rain are you getting or is projected to for you to receive? And if there's wind out there, there's going to be a different type of accumulation as opposed to if it's dead calm. But you get that ice put on every surface of your tree, of your branch, of your twigs, and it changes branch mechanics. It increases the diameter, so that means it can have more accumulation. It increases the volume and surface area. It increases stiffness, decreases flexibility, and increases weight a great deal. And of course, the drag coefficients with the wind go way up. Here is tree crown reconfiguration values. This is normal for just wind, but when you have ice on the tree cannot reconfigure as effectively, and so it starts to have its brittle reconfiguration, breakage, much earlier at lower wind speeds because the ice is keeping it from bending. We also have some nice stuff that deal with tree mortality and probability. And remember, if we approach the 4 inches, and the record for the eastern United States is actually 5 inches of accumulation in radius on some tree parts and some, actually those were power cables. But you can see that ice thickness in millimeters, as it goes up, we have tremendous tree catastrophic failures. So what I did was looked at a whole bunch of data from Eastern North America and identified the damage cause. And if you notice ice thickness and weight, elevated wind loads, ice load duration, how long it stayed on there, and you get a bunch of creep that pulls the branches permanently down. Tree life form just means evergreen, deciduous, that type of thing. The only thing that we could do something about as arborists, we can't change the weather, but asymmetrical crown, that was the highest rated tree ice storm damage that we could do something about, asymmetrical crown. Now for ice storms, future climate variability, as we get more warming, we're going to get the polar vortex weakening. And that means these fast-moving Arctic fronts swing down over Canada and the United States. And if that's the case, we're going to get a few more ice storms. All right. So that's our load. All right. That's our load on our trees. What's our impact on our trees? Well, I'm going to hit a couple of them. In the last 5 years, there's again been tremendous research that and many of them funded by Tree Fund. And so always pay it forward and give to Tree Fund, because some of those researchers are doing fantastic things, all in the last 4 to 5 years. I pulled out a couple of those research things that are very interesting. One is wind shifts the material allocation in trees. It changes height to crown mass to stem root base ratio. It changes that, just the wind, just being in the wind. So we get more taper with wind, more structural roots, and we develop stability. We have less height and less crown mass. We get stability. We, in arboriculture, we can change a bunch of those things. We can manage trees to help them shift to better withstand wind. So if you take a look at my tree here, crown mass, stem height, and stem base to root plate combination, if we decrease height, we have a tendency also in the wind to decrease crown mass, and we build taper. So if 1 and 2 go down, 3 goes up. Here is tree height and wind throw. we've got some diameter across the bottom. And in this case, our tree height to diameter, or slenderness, we'll talk about slenderness later. We have a stable area, but if we get a lack of taper, we can have bad problems. This is relative stem diameter and how many years. In over 5 years, where we locked a tree down and kept it from moving, and that's the only thing that changed. We kept it from moving. In the wind, it developed tremendous amount, in a relative sense, of stem base. The tree is changing its allocations. Another place that research has been helping us is wind damage and crowns. If we have more crown mass, branch mass, crown mass to stem mass ratio, the crown is getting much heavier compared to the stem, we get damage. So the more crown mass, the more damage we get. The greater that mass's center height in the tree, the more damage we get. The smaller the live crown ratio, especially at the end of a big height, we get tremendous damage. We get more large branches, especially up high where they're the same size as the stem is where they're hooked, we get damage. And then of course, even as we saw in ice storms, more asymmetrical crowns, we get damage. The asymmetrical crowns are killing us out there. This is wind throw probability. And I marked out, remember across the bottom, that's branch or crown mass to tree mass ratio in percent. As we start to get the crown mass approaching 42% of stem mass or tree mass, we get 50% of those wind throws. This was a great graph these researchers generated. Another group looked at critical wind speed and center of wind load. Where is the center of wind load? The higher in the tree it is, the less critical wind speed the tree can handle without breaking. So at 50% of the tree's height, if that's where the center of its wind load, its crown mass wind load is centered, that is where we can handle about 62 miles per hour. But above that, we're going to be rocking and rolling with that particular tree. So if you have more base weighted trees, we can handle higher wind speed. If we have more end weighted trees or branches, we can't handle very much wind load. It's too heavy at the end. So what can we do as arborists? Well, we can do some crown raising. The little blue mark is the center of wind load in this crown mass. And these numbers down here are a calculation. And don't worry about the actual, or worry about the percentage for this presentation. You notice that as we raise 1/3 to 2/3, we are decreasing the actual sail by about 53%, but we are raising the mast to the very end of this long lever arm, and the center of the crown mass is way up there. What if we do a reduction? Notice that if we go 1/3 to 2/3 reduction, which is not a biologically viable thing, but if we did that, notice that we reduce sail by 88% in these trees because we're reducing. The point of this, and you're saying, please, Kim, let there be a point. My point here is that reduction works very well. Raising does not. Now let's look at taper. This was another a number of researchers do some good information on taper or slenderness. Slenderness, for most trees that are self-supporting, it's really only critical with asymmetrical crowns and large branches. That's when we can get a lot of damage due to lack of taper or slenderness. Total height is usually more important than taper for most trees. But the rule of thumb is the less taper you have, the smaller the bottom is compared to the height, we get damage. So you want a strong taper that's 55 to 50 or less height to diameter, and you want good base rigidity. That way you get a stable tree. This is critical wind speed that could lead to damage, and this is its slenderness ratio. Remember, that's height to diameter. And notice that at very slender, very small height to diameter ratios, we get damage at fairly low speed. Slenderness, this is another way. I didn't cite this. I think this is Matic's work from 2015. But again, there's height to diameter around 55, and there's where you get trees standing or trees failing. I encourage you to go to these literature citations and look them up. Don't believe me on any of this. You go look up what the researchers have found as both their facts and what they have developed as their truths. Another area is tree porosity that we don't really look at very much. The windbreak people do. But if you have more crown density, we have a tendency to have more damage in wind load. If you can reduce frontal area and increase porosity of the crown, like through thinning, we can get a stable tree. But there is a problem between optical porosity that you can see and the actual aerodynamic porosity that the wind, is it moving into the crown and through, or is it just piling up and moving around? About 40% aerodynamic porosity, beyond 40%, that's when we can actually reduce drag coefficient. Up to that point, we're increasing drag coefficient. That's why a tiny bit of thinning doesn't work at all. It makes it worse. So the most drag that you see in a tree is those leaf flags way out on the ends, end-weighted branches. So here's a little experiment for you. This is optical porosity in 10% area. And notice that the shaded area are the leaves. We go from an optical porosity of 10 up to 90, and probably at 90 the tree's dying or dead anyway. But that is optical porosity. But what we're interested in is aerodynamic porosity. And as we increase at the very start aerodynamic porosity, we increase drag coefficients. There's more pressure energy being placed on our trees up to a certain point. And then it falls as we get more and more crown that's porous. Another thing that we need to pay closer attention to, we have a lot of understandings about bending, but not torsion or twist. If you take a look, tree parts twist preferentially. They do a little figure eight or a circle. They would rather twist at least 1.5 times more twist than bend. But yet we look at a lot of bending. And if you have a part under torsion, it does not have the flexibility it does when it's not. So if we get more torsion, that means less critical bending load can be sustained. If you have more torsion, you have more longitudinal faults. cracks, longitudinal cracks. Most of those come from twisting faults. So more height of the tree, there's more room for branch and stem torsion damage. This is something that we should all pay attention to, is torsion stress versus bending stress, because it's a trade-off between how much torsion, how much bending, and where do you break. There's the average breaking load for trees. There's the minimum breaking load for trees. Another thing is tree drag coefficients and Vogel exponents. We have had a lot of work in the last 5 years. Frontal area and drag coefficients, they go together. You just don't have a drag coefficient with a tree. You have a frontal area and a drag coefficient because it's a combined effect. That's why we use a Vogel exponent. So less than 16 miles per hour, we get quite a large variation in drag coefficient because we're just being pushed around and swaying and everything else. Above about 67 miles per hour, our drag coefficient pretty much levels out and becomes constant. Now the Vogel exponent that I mentioned, that is the decay in drag coefficients by caused by reconfiguration. So instead of a wind speed to the square, it's wind speed to the square minus the Vogel exponent. And for an example, the frontal area of a tree in one-sided case was reduced by 60%. 60% of the frontal area receiving wind load was reduced by 60% in a 45-mile-an-hour wind. Now, the frontal area, this is standard geometric crown shapes, and FA means frontal area. These are relative frontal areas for the shape of your crown. Now, this is based on a right cylinder. There's a square, a box down at the bottom there, but it's the green outlines. What's your frontal area? What does your crown look like? Here are drag coefficients based on those shapes. In gymnosperms, this is the average that we're seeing from the literature. Angiosperms that are deciduous and angiosperms that are evergreen. The N number is how many different citations that was. Here's the minimum drag coefficients, the minimum after you get to this miles per hour on the right-hand side. And let's just take, there's 100 miles an hour at the top. At 100 miles an hour, in one group, they found that the minimum drag coefficient was 0.161. Vogel exponents, theoretically, there would be a minus 66. But if you take a look at both evergreen gymnosperms, deciduous angiosperms, this is respectively either 7 or 9 different research groups finding these Vogel exponents. The wind squared is not a square. You have to reduce the square by this number. And younger trees are more flexible, and so they have a bigger negative number. All right, take a big deep breath, sigh of relief. We're almost done. Trees are going to fail on you. No tree lasts forever. You can go to the sequoias and the bristlecones, and they'll outlive us. But again, all trees fail. And the tree treatments that we have for wind stability make them a little bit less risk. So what can we do? We can remove asymmetrical crowns. We can help with small live crown ratios. Sometimes that's removal. And leans. Asymmetrical crowns and leans are hideous for us. We can reduce height, reduction. We can reduce frontal area, abridge those branches, shorten those branches, don't remove them. because of damping. We have excess nitrogen and phosphorus has a tendency, cited in 2 cases, of causing damage. So watch out on your excess nitrogen and phosphorus fertilization. Crown mass reduction, soil compaction reduction. That makes things more wind firm. Cultivate larger tree tapers where we can. No stem root-based damage, viable root space, give them plenty of room to live in. Ecologically viable root space. And then good soil drainage. Don't suffocate your roots. Then abridge branches. Don't cut them off, abridge them. If they're not going the way you want to, don't slice and dice them, just abridge them, shorten them. The rule of thumb is pruning and health management programs reduce wind damage. We know that, we've seen that, we've measured that. Pruning and health management programs can reduce wind damage. So our tree secret, managed, pruned, cared for trees are better prepared to stand and survive wind loads. Tell your clients and get your clients to make sure they understand that you're just not coming there to keep your family fed and to make them look pretty. You are doing risk management for the long term by managing, pruning, and caring for their trees. You have better trees, you have less risk. Thanks for paying attention.
Dr. Coder, thank you for a fantastic presentation. As I noted in the chat comments, it's very timely, at least for those of us either on the Gulf Coast or on the eastern seaboard with hurricane season starting today. So very, very timely. Thank you. We do have a number of questions, but since we're very close to the top of the hour, I'm going to go ahead and launch the poll for those of you that need to jump off the call, but we'll stay on for a few more minutes and get through a few questions here. And there's a number of them. We're not going to get to all of them, so I'm just going to go ahead and apologize to everybody. There's one here that I thought was very good. It says that a study out of Florida rated a lot of southern tree species for the ability to withstand hurricane-type winds, and they rated it from kind of highest to lowest. And it was a study, I think, done by Duryea and maybe Gilman back in the mid-2000s. And their question is, do we have anything newer or anything that's looking at temperate tree species?
We have little pieces. We have more information in ice storms by species than we do in windstorms by species. And remember, the windstorms, if you do not control by where it's located and what its neighborhood is, it is unclear that that means anything. So you've got to be very careful. If we have, for example, live oak on the coast that's short and squat and has no neighbors versus a forest type tree, and there you can have forest morphology in dense green belts, downtown areas. So we've always got to be careful about, can we control for all the other features than just species? If we can, then those lists mean things.
Yeah, very, very good. We have another good question here. They ask, this one came from Mr. Moreno, and he asks, are root depth and root plate symmetry factors in wind throw?
Absolutely. And there is a fist fight occurring between some groups because they have different soils that they measure. And it's the difference between root plate width versus root plate depth. Because the taproot and root plate depth stuff, for many soils, the depth doesn't matter unless it's a well-drained to moderately well-drained soil or a coarse soil. Because if you hit any kind of water limitation down below, it is the root plate width that has more impact. And then the symmetry is that we want to have extended at least 2 or 3 nice big roots out to windward versus our more massive roots that prevent bending to leeward. So the windward goes out a ways, the leeward is fairly close where you get a lot of diameter growth because it has to prevent hinging and bending. The side roots off to the side of the direction of the wind, they're actually under torsion and twist. And again, when we trench around trees, damage soils and their roots, we set them up to fail.
Absolutely. And kind of the other piece of that puzzle is soil liquefaction. So when you add that rain event,
the plastic limit and the plastic limit and the liquid limit on soils, especially if you have a little bit of clay in that soil, can be devastating. Now, some people say, well, in a big flood and there's water over the top of the soil, I have extra weight. That's true. But when you have a sail that high in the air under that load, we get a lot of tree toppling because the tree and the soil, they just can't hold together and they fall down. So these old soil components of liquid and plastic limits, we need to pay attention to them because some places in the United States, in the eastern United States that I looked at, and I didn't put it in this presentation, have received 20 to 30 inches in a 24-hour period. That causes the soils to fall away from the tree roots as the trees are pushed.
Absolutely. I mean, we see it down here on the Gulf Coast. We lose more trees when we have heavy rain events followed by winds than a lot of times occurring at the same time.
And
Dr.
some places we call that squall fall, where you'll have especially dry conditions, and then all of a sudden you'll get a squall line come in quickly and douse everything with water. And then under fairly low wind loads, everything pops over.
Yeah. We see that a lot here on the Gulf Coast, at least on Alabama's Gulf Coast. Dr. Coder, we are past the top of the hour, and I want to be respectful of everybody's time. Thank you very much for a fantastic presentation. We certainly missed it at the Southern Chapter Conference this year, but thank you for sharing it during today's webinar. I also want to thank everybody who tuned in. We had a great audience today. I apologize for not getting to everybody's questions. Couple housekeeping notes. Remember to send us your certification number if you did not provide it during registration. For those of you needing SAF credits, I saw a few notes pop up. We will be submitting those on your behalf to SAF. And I think we did have all of you provide that during registration, so you should be okay. And finally, don't forget to support Tree Fund. We have to remember that a lot of the research that we see in the field of arboriculture, a lot of times it's ended through some of the seeds that Tree Fund and some of those small grants that come out of. And we try to continue to grow those grants. So, you can go to the Tree Fund webpage, go to the donate tab. It's a great way to continue to support these webinars, to support the future research and support of our industry. Dr. Goder, any closing thoughts for us or comments before we close today's webinar?
Well, think safe, think health, and think trees.
Perfect. Thank you. With that, thank you, Russell and Monica, for being our co-moderators today. And thank you, Rusty, for being our IT support here at Auburn University. So thanks all. And don't forget to join us next week. We have a great presentation on, help me out, Monica. Who are we hearing from next week?
We have Rachel Entwist. She will be fighting microbes with microbes.
Yes, should be a totally different topic, which is what I love about this webinar series, coming from the UK, so a different part of the world. So should be a great presentation. So join us next week on June 9th. With that, everybody, thank you. And Russell, do you have any closing comments for us from our CEO here at Tree Fund?
I'm very appreciative of both Dr. Coder and all the participants. This was really great. Thank you.
Well, thank you all and have a good rest of your week. Cheers.
Dr. Coder, thank you so much from everyone here. You did a fantastic job.
Thank you very much.